Hello! Now we're going to finish the tutorial to simple assembly for the x86-64 instruction set architecture. Part 3 covered conditional and control flow instructions to implement branches and loops. Part 4 will explain now how to implement function calls. Our discussion today aims to complete your orientation toward understanding and writing assembly source code for the x86-64 ISA by learning how to make function or procedure calls. To understand the mechanism for procedure calls, we first need to understand the call stack. The notion of a call stack is a dynamically allocated memory region that grows like a stack data structure. That is a last in, first out, or LIFO discipline. The x86-64 call stack grows down toward smaller addresses. Some ISAs have stacks that grow up, and some allow software to decide which direction the stack grows. The general purpose register with a mnemonic RSP holds the current address of the top of the stack. When the stack grows down, this is actually the smallest address in the stack. All legitimate stack accesses will be greater than or equal to the RSP. The main way to add elements to the stack in x86-64 is the push instruction. Push Q decrements the RSP by 8 bytes and then copies the source operand to the memory location of the stack pointer. The operand can be an immediate, register, or memory operand. Typically, it is a register. Removing data from the stack can be done with the pop instruction. Pop Q copies the 8 bytes located at the memory address in RSP into the desc register operand and adds 8 to the stack pointer. Here are two procedures we'll use to explain the general idea. The mult store procedure has 3 input parameters, 2 longs and a long pointer. It makes one procedure call and it has no return value. It calls the mult2 function, which takes 2 long arguments and returns a long. The disassembly is shown, and we'll walk through how it works. We'll start by looking at how control flow goes through a procedure call. A call is made by first saving the return address to the stack, and then jumping to the label at the start of the procedure. In x86, both steps is accomplished with the single call instruction. The return address is the address of the next sequential instruction in the program after the call instruction. A procedure returns by popping the return address from the stack and jumping to that address. Both of these steps is accomplished by the ret instruction. So let's have a look through the disassembled code of our two procedures. Here we can see that the instruction pointer points to the address of the call Q mult2 instruction. The stack pointer is at some value 0x120. So the call Q increments the stack pointer by 8 and pushes the next instruction's address to the stack so that the procedure call will return to the next instruction in the program following the call. The call finishes by changing the instruction pointer to the address of the mult2 label, which is the address of the first instruction in the sub-procedure. Now, when the sub-procedure reaches the retq instruction, it will pop the return address from the stack and replace the instruction pointer with it. This will cause the processor to resume fetching instructions back in the first procedure at the move instruction that follows the call. Now that we have a handle on the control flow, let's talk about the data flow for a procedure. This consists of how the procedure gets its arguments and how it returns values. This is determined by the calling conventions. First, the arguments. The System V calling conventions we use allow for passing up to 6 64-bit arguments and registers. These will be used for the first 6 arguments of a function in the order listed: RDI, RSI, RDX, RCX, R8, and R9. Additional arguments beyond those 6, or arguments that are larger than a quad word, get passed by pushing them onto the stack in reverse order. So if there are n greater than 8 arguments, you would see a stack something like this, where the nth argument is pushed first, then the n-1th, and so forth, and the last argument to get pushed to the stack is the 7th argument. By the way, the call instruction would come next, which would push the return address after all the arguments. For return values, a 64-bit or shorter return goes through the RAX register. A return value between 64 and 128 bits can be returned by combining RDX with RAX. Floating point values get returned in the XMM registers, and larger return values such as structs are returned by the stack. More typically, though, a function will return a pointer to a struct by the RAX register. Let's see how call and return values work in our simple example. To make the call to mult2, first the caller has to make sure that the arguments for A and B are in the first two argument registers, RDI and RSI. Here, since mult_store is passing its own first two arguments, they're already in the right registers. RDX is a caller-saved register, and its value needs to be used after the call. So mult_store copies from RDX to RBX to save the value of dest. RBX is callee saved, so its value would have to be saved to the stack before writing to it like this. Then the call is made to mult2. There it knows that its input arguments are in RDI and RSI, so it does its calculation, putting the result in RAX, which is the return register, so it can just return. Note that retq is essentially the same as ret. It just specifies that the return address is a 64-bit instruction pointer. When the call returns, mult_store knows that its variable t is in the RAX register, which it stores to the address of dest. Here again we have the full set of general purpose registers, color-coded to show which are callee saved and caller saved. Remember that a callee saved register needs to be saved in a function before modifying it, and restored to its original value before returning. A caller saved register needs to be saved in a function before calling another function if the value is needed after the second function returns. Typically, these registers are saved on the stack, although they can also be saved in a register of the other kind. That is, a caller saved register can be saved in a callee saved register, and vice versa. Sometimes a function will do that by saving a callee saved register like RBX at the start of the function, and then using RBX to save some caller saved registers that need to survive a function call. Now we'll look at a simple recursive implementation of the popcount function we used to study loops. Here's the high-level code and the assembly implementation. The basic logic is to mask the least significant bit of the input argument with 1 and add it to the recursive sum from shifting the input by 1. We'll walk through each part of this function. Here is the recursive base case. We're done when the input variable is 0. So first, the return value is loaded with 0. Then testq is used on the RDI argument. Remember, this does a bitwise AND. The only number ANDed with itself that results in 0 is 0. The JE jump equal instruction jumps if the 0 flag is set. The jump target is L6, which just returns from the function. Now let's proceed if x is not 0. Since we're going to be using the RBX register, which is callee saved, we first need to save it. So it gets pushed to the stack. Now it sits just below the return address of this call. We can use it to preserve the value of x and 1 past the function call. So now we calculate the value of x and 1 into RBX and shift the input argument right by 1. So now we can make the recursive call, and the value of x and 1 will still be in RBX when it returns. We add the value in RBX to the return value of the recursive call and put the result into the RAX register to return it. We have to restore the previous value of RBX from the stack, and then we can return. You may like to walk through a small example and try to keep track of the values in the stack and registers. For example, try to track through what happens when pcountr is called with an initial argument of 4. That wraps up our introduction to basic assembly. This should be sufficient for you to be able to read and write basic assembly programs. Operating system and compiler writers need to go deeper still.